Hi, my name is Reyne from the University of Sydney. As I mentioned in the sample B recording, I'm going to speed up the process for the remaining ones. So I'm going to jump straight into it. We're looking at sample F. Now, first of all, we want to think about these tests. We're testing for a double bond or a triple bond in our unsaturation tests. And it's telling us that there is none of those around. Our orange color remains. The oxidation tests, we're hitting it with acidified potassium dichromate and the solution turns green. So that must mean that there is an alcohol or aldehyde present. All right, key piece of information to know. Finally, we test for carboxylic acid using sodium carbonate, and there are no bubbles, so we can cross that one off. It's not something we have to deal with. Now, as with before, rather than diving into the IR or the mass spec, I'm going to move down into the carbon and proton first to help me kind of elucidate what's going on. And then we'll come back to those to try and confirm a few things. Now, first of all, our carbon NMR has two peaks, right? So let's label this 1 and 2. But what's key to note here is the location of these. Now we've got one peak, so peak 2 is under 20. Now that kind of suggests to me that it's more of an alkane sort of space in that it's not next to something that is going to be very electronegative. So there's not something that's pulling electron density away from that carbon and de-shielding it. Up at about 60 though, peak number 1, that's been de-shielded. So it's telling me that it's next to something that is going to be pulling electron density away. We've already established that there must be an alcohol or an aldehyde present, and both of those could do that. So it's telling me that peak number 1 is the carbon that's right next to an oxygen, and peak number 2, there must be another carbon away, not that influenced by the oxygen. Carbon out of the way, let's move into the proton. Now this proton is lovely to see because it's quite clear. You know, if we kind of zoom in a little bit, we can see here that we've got a nice triplet. We've got a quartet over here at about 3.5. And then we've got a singlet down here at about 4.5. So if I label these, right, A, B, and C, and then if we come down to the peak data down here as well, and we'll label these the same, A, B, and C, so we'll reuse these labels shortly, we can pull out some information here. The triplet, having quite a low ppm, is suggesting that it is similar to before, not near something that's de-shielding. Whereas we can see the quartet has moved a fair way down the ppm. Its chemical shift has moved downwards. So it's likely to be close to something that's de-shielding. The singlet can be a little bit tricky to kind of think about. Now, one thing that can maybe spark in your mind though, when you see a singlet and the possibility of an alcohol being present, that's often a good guess to start with, because the proton on an alcohol tends to be a singlet. It doesn't tend to interact so well with your carbon chain protons. So that's a little clue that we'll come back to. We can also see that there are a certain number of protons present as well. So the singlet, there is only one proton in that environment. The quartet, there are 2 protons there, 2 hydrogens. And then in the triplet, there are 3. And this is another clue. So if we think about the environment where there are 2 protons there, we're seeing a quartet, which suggests that it's next to something with 3 hydrogens, the N+1 rule. Vice versa, the triplet at about ppm of 1, peak C, that has 3 hydrogens, but we're seeing a triplet, which means it's next to something that has 2 hydrogens, hence a triplet, the N+1 rule again. So that tells us they must be next to one another. It confirms what we kind of thought in terms of the carbon NMR, if we have some maybe terminal carbon, and then a middle carbon, and then something like an oxygen that's pulling electron density away from that middle. So let's start to try and confirm this then. If we think about, first of all, our mass spec, Our mass spec, we've got a molecular ion of 46. Assuming the simplest case, we know that we have 2 carbons, which would be a total of 24 to account, right? 12 each. We know that we have a total of 6 hydrogens, which would be 6. All right, and we get that from that idea of the peak area ratio. So we're taking the simplest route, we're assuming that this is the number. And that brings us to 30. And the other piece is that we know that there's an alcohol or an aldehyde present. Now, in the case of either of those, there must be 1 oxygen. So we times it by an oxygen, that's 16, and that adds up to 46. Good news, okay? Good news. Now, I mentioned in the sample B video that it's hard to pull out fragment information on a mass spec. Sometimes it's possible though. Now here is a case, right, where let's just assume that it is an alcohol. You know what? We're not going to go into the fragment information. I think it's better, and I encourage you to do this as well, is to try not to spend too much time looking at fragment information, because it can just be a nasty spiral to go into. We'll instead turn to IR, which I think has a bit more reliable information. Now, as we see often, and we saw in previous examples, we have a peak at about 3000, which is likely to be our C to H stretch. We have peaks at about 1450-ish, 1500-ish, which is going to be our C to H bend. And then we've got this whole big fingerprint zone, which, as I've said before, I encourage you to not spend too much time on. Your carbon-carbon stuff is likely to be in there. It's kind of hard to pull apart. But there is one other peak that we haven't talked about yet that's quite important. And we can see this peak here, okay? And that peak, if you have done sample B, that peak was not there whatsoever, all right? This peak is gonna be our alcohol. Now, if we were looking for, say, an aldehyde, we'd be looking for a carbonyl peak, C double bond O, and that would be about 1700 in terms of its wavelength, and that is definitely not present here. So this is where we can really say, well, this must be an alcohol, it can't be an aldehyde. Now, if you're wondering why the peak is very broad and why some peaks are sharp, in the case of an alcohol, because hydrogen bonding can occur, it results in a whole bunch of variations in terms of the peak that could be formed. So rather than having a sharp, there is only one possible outcome, we have a broad peak to represent that there are many small variations in how the hydrogen bonding can affect that peak. Okay, with all of these things together, this one I think is pretty straightforward. We have 2 carbons, we've got an alcohol, we know the order that they're in. This is telling me it must be ethanol, okay? And if we kind of go back through our logic here, and I'll change color to make it stand out a bit. Peak 1, remember if we said from peak 1 in the carbon NMR, it's de-shielded, it's gone further down in its shift. This must be the one that's right next to our alcohol. Therefore, peak 2 would be further away from our alcohol and not being de-shielded. There's a bit of a waterfall effect, a little bit of overflow, but largely we can see that peak 1 has been de-shielded considerably. If we then change to think about our hydrogen environments, we had the 3 different peaks, the singlet, quartet, and triplet. As I said before, the singlet is often a safe bet that it's going to be on an alcohol, okay? And that kind of is due to the fact that an alcohol proton doesn't tend to split or interact with the carbon protons that we see next to it. The quartet, however, tells us that it must be an environment that is next to something with 3 protons. And it also even says in the peak area ratio that there are 2 protons. So we can say it must be that environment there, which then leaves our terminal carbon to have the proton environment C. And that kind of wraps it up. All of the different tests, all the different pieces of evidence come together to that. Cheers.